Hello and welcome to another episode of the Oxford Online Maths Club. Nothing happened. This is always technically perfect. Live stream never has mistakes. My name's James, and this week I'm joined by Alice.
Hi, everyone.
Alice is here to talk about topological graph theory and of course, kind of computer science point of view. I'm really excited. Say hi to Alice in chat. If you're joining us for the first time and you'd like to join chat, you can join over at slido.com/OOMC or go to slido.com and put in the event code OOMC. If you do that, you can be anonymous in chat, or you can set a unit's name like people like Shrish and A and Neutrino have. They say hi. Aya says hi in chat as well. Hello to people in chat. While you're saying hi, I will do our normal poll for how was your day today? And I think I'll also ask Alice. Alice, on a scale of 1 to 5, how was your day today?
I think my day is a 5 now that I get to do this really fun live stream.
Brilliant. Okay, good. I've never been brave enough to do the before and after poll to find out if doing the live stream has
Yeah.
improved people's days or not, but that's already a vote of confidence. Right, okay, people are voting on how their day is. We're currently at 3.9. Meanwhile, Shrist says hi as well in chat. So it's good to have people in chat. And people are doing exams. I understand there's exams because it's May and June for exams, especially international ones. So people have got physics and chemistry, and there's some discussion in chat about papers and things. Morgan says hi, Alice, and it says that they want to study computer science and maths at university. I can't remember. Is that what you're studying at university, or is it slightly different?
Yeah.
Okay, no, that is
Yeah, so I can do a quick intro
yeah.
about who I am and what I'm studying. So I'm Alice. I did my undergraduate degree in Canada, where I studied computer science. And actually, so in high school, I thought I wanted to do medicine. Then I spent some time volunteering in a hospital and decided that medicine was not for me. So I thought I wanted to be a software engineer. So I went and I studied computer science, and I ended up doing a specialization in math because I had enjoyed some of the courses I took. And in that specialization, I took courses like topology and group theory, and things that normally an undergraduate computer science student might not have to take. And I really, really fell in love with this more what I thought was abstract math. So now I'm at Oxford. I'm a master's student, and I'm doing math and computer science here. Yeah, so that's kind of my background. So I studied computer science, and now I study math and computer science, and I'll be studying computer science next year too.
Cool. Okay, so masters is the kind of normally in the UK, masters is 1 year, and it's something you do
Mhm.
after an undergraduate degree. For context, you're saying you're doing computer science next year as well. What's the plan
Yeah,
there?
so I'll be doing a DPhil, so a PhD in computer science. Uh, But surprisingly, a lot of these math things end up cropping up in computer science in ways you wouldn't expect. So hopefully today, I'll kind of show everyone how topology comes up in what might normally be considered a problem for a computer scientist to solve,
Thanks, and that's a
or a
really
field
good. I think
that's,
that's a
yeah.
really good introduction and segue into talking about topology. So I think computer science takeover. Alice, take it away.
Okay. Okay, cool. So I don't know how much of a background people might have in graph theory, but just in case there's people here who have never seen it, we're going to start from scratch and assume that people know nothing. So we'll start with sort of an interesting question, so just something to think about. And that's, what do the internet, your brain, all of the people you've ever known, and the city that you live in have in common? Well, if we think about it, the internet consists of different computers and electronics and whatnot that all talk to each other through live wires, actually, through physical wires, um, like this. So kind of looks like that. Your brain is a bunch of neurons, and all of these neurons also communicate with each other and talk to each other. So they kind of have the same structure. So if this is a brain, it's kind of hard to draw an abstract brain, but and what about the list of people you've ever met? Well, if this is me, And suppose this is all the people I've ever met. So suppose I haven't met very many people, just 4. And then they've all met people. And maybe some of those people know each other. Well, then we also get this sort of network structure. And the same thing with the city that you live in. So I might have a bunch of houses and parks, and they're all going to be connected by a network of roads. And where I'm from, which is Canada, the roads will very often look like grids. But in other places, like the UK, some of the older roads are more random and are not necessarily grids. And so the whole idea is that all of these things are networks between objects that are related to each other somehow. And the nature of those relationships isn't the same depending on the network that you're looking at. But we might be interested in studying all of these networks all at once and deducing fundamental properties about these networks without worrying about certain details of them. And so that's the idea of graph theory, is we study networks in this abstract notion. And they crop up very often in computer science. So if you do end up studying computer science as an undergrad, for example, you will very likely take a course in graph theory. So we'll start with the definition of a graph, as a typical introduction to graph theory course might define it. But I'll stop for a second and hope that everything makes sense and no one has burning questions yet.
People in chat a moment ago guessing what these things have in common, and people have said networks and relationships. I think we had an episode. Oh gosh, was it about a month ago? We had an episode about friendship networks of people joining things together. Maybe people have seen networks in that one as well. I think though, with thanks to Rory, who is moderating chat behind the scenes as well. Thanks, Rory. I think let's go for a definition, or go for the. I think we're ready for a
cool.
math definition.
Yeah, so we'll chat a little bit more about why we might care about graph theory in a little bit, but we'll start with a definition so that we all know exactly what we're talking about. So intuitively, a graph is just a finite collection of elements, which we like to call vertices or nodes, and they're all connected by edges. And so it's this abstract way of representing a relation space or a network where edges define who's related to whom, whatever the nature of that relationship is. So for example, this is a graph, and note that a graph doesn't have to necessarily have one component. It can have multiple pieces. This is a graph, etc. So we say, let me try to make my pen a little bit thicker. So a graph, the graph G, is that sort of visible? Yeah. Okay, is a pair, and we're going to call it V and E. And we're going to call V is just a finite, meaning we don't have infinite elements, even though we can think about infinite graphs if we want to, but we won't go there. A finite, non-empty, meaning we have at least one vertex in our set, set of vertices. And you can think of a set as just a bag of objects. So we don't really care about the order of them, and we don't want to repeat things, but we just list them out. And we're going to define E as subsets of pairs of these vertices. So we define edges as being a subset of U, V, where U and V are two vertices. So I think to understand this definition, it's going to be very useful to look at an example. So let's draw a random graph and sort of deduce what V and E might be. So I might have a graph that looks like this. So let's say I have a node here, 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 and here. And we'll call this A, B, C, D, E. And let's throw some edges in here. So we might have an edge between A and B, an edge here, 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 and here. So this would be called a cycle because it's like a cycle around the graph. And let's add two more. So we might have an edge here, and we might have an edge here. So in this case, if anyone can guess what our vertices might be, brownie points. So it's simply A, B, C, D, E, or whatever we might call our vertices. So in a social network, this would be people or profiles. In this case, we're worried about graphs in the abstract. So we're just calling our vertices A, B, C, D, E. And our edges are going to be pairs of these vertices. So we might have an edge between A, B. We see that we have an edge between BC, CD, DE. We also have AE. And we also, at the very end, we added BD and CE. So hopefully that makes sense. A few things to note is that in this case, we're just denoting pairs without worrying about the ordering of the pairs. So we can also define, for example, directed graphs, where we might have two vertices and an edge and a direction between them. We can also define multigraphs, where we have vertices with multiple edges between them, or even self-loops. So a vertex might have an edge that goes to itself. So things can get really fun and complicated and complex, and you can model all kinds of cool things with graph theory. But for today, we're just going to stick to relatively simple graphs. So undirected, no multiple edges, no self-loops, just plain old graphs. So another interesting thing to note is that in this abstract definition of a graph, where we define the vertices and the edges, we don't really talk at all about how we draw that graph. And how we draw that graph is up to us. And the same graph can have multiple drawings. So, for example, if we look at the graph that I drew previously on the plane, if we picture the edges as strings or elastic bands that we can move around, we can pull an edge out and redraw the graph like this. So if we were, for example, to look at this edge right here, then what we could do is redraw our graph here, B, C, D, E. It's a terrible C. And we can have all the same edges. Oh. Like so. And then we can take this one edge and maybe pull it out and around. And so we've redrawn our graph. And the edges that were previously crossing here at this point in the middle are now no longer crossing. And so when we can draw a graph on the plane like this without having any edges cross, we call it a planar graph. So in this case, this is a planar plane. Sorry, my Apple Pencil is lagging a little bit. A planar graph.
Alice, is I suppose the first one in the orange is the first one you drew in orange. Is that also a planar graph?
So technically it is, because it can be drawn without edges crossing.
I see. Okay, so it's kind of planar graph in disguise, but it's not obvious when you look at it that you could rearrange the edges. I see. Okay, because I guess they're in the abstract sense they're the same graph. So
Yeah.
Yeah, I think you have to decide whether you could rearrange the edges until, oh, right, okay, now none of them are crossing in the plane.
Yeah,
Interesting. Okay.
exactly. And this is not always an easy problem to solve. So for example, if I were to draw a graph like this, so use a different color. So suppose I have two vertices like this, and three over here, and I fully connect each vertex to each edge. So is this graph planar?
I think that's a
Do
question for.
people
I think
think?
that's a question for chat.
Yeah. So do
um,
people think this graph is planar?
it's got. I can see 3 bits where lines are crossing on the board, so I'm highly skeptical. Morgan in chat has maybe seen an algorithm for this and can see how this. Um, so Morgan in chat has used the word algorithm, which is, I think, a hint of a link
Mm-hmm.
to some sort of traditional computer science ideas. Somebody else who's anonymous, which you can be in Slido chat, you be anonymous, says, "Wow, this isn't." And then their guess of what computer science is Photoshop and Visual Studio, which I'm not sure is my take of what computer science involves. I think computer science means a lot of different things to a lot of different people in a lot of different places. Uh,
Yeah,
okay.
certainly.
We've got one vote in chat so far for no. This is not a planar graph, which I suppose is them saying
Mm-hmm.
that no matter how you move the edges around, there will always be some edges that cross in the plane. And Imo's got a kind of question. We've got Maya votes for yes, but Imo's got a question. Are you
Yes.
allowed to move the points as well? You've talked about moving the
Yes.
edges. Can you move the points?
Yeah. So you can move the points and the edges however you'd like.
Can I
There's
ask,
no restriction there.
can I ask a really hard question? Does it? Do you ever need to move the points?
Hmm.
So I think Imo's imagining.
Uh,
Imo might be imagining a way to move the points around, and
yeah.
then the mischievous thing for me to think is, well, could Imo just have achieved that effect by moving the lines in a kind of maybe slightly weird corresponding way? I don't know.
Yeah.
I'll have to find out.
So if people are ready for the answer.
We've got about 4 votes for yes now. To say that maybe
Yes.
this is planar, which would be
Yeah,
easier to prove because I guess you would just demonstrate that you
exactly.
can redraw it with the same connections but nothing crossing. Okay,
Mm-hmm.
back to you.
Yeah, exactly. So the answer is yes, this is a planar graph. So there's a few ways to see this. So what James was wondering is, can we see that this is a planar graph without moving any edges around? And the answer is yes, we can do that. Without moving any vertices around. So the answer is yes, we can do that. It's easier to move vertices around, but we can show both ways. So one thing we can do is redraw our vertices exactly as they were. And we can redraw some of these edges. But instead, we can always maybe pull this edge out and pull this edge. Oh, hold on. 1, 2, 3. Pull this, right. Yeah, pull this out. Yeah, and pull this out. Alternatively, it might be easier to visualize moving the top left vertex and sort of pulling it down like, oh, it's kind of hard to see, but pulling it down like this. So we can redraw it like this, where we have the middle 3 vertices and one like this. And this is the same graph. So the answer is yes, it's planar. And when we have a planar graph, you can often just redraw it and then show that, look at that, no edges cross. Now, what about this graph?
These are all the
So,
same graph. The graph theory is hard, partly because these 3 things look quite different, and they're all the same. Okay, next one.
yeah. Yeah. So the math lingo would be that we call them isomorphic. So
Same.
they're graph twins.
Iso means same. Morph means shape, I guess, and then maybe shape has got some not the same shape when you look at them, but the same kind of spatial. I don't know.
Yeah.
I'll stop trying to
But
do
morphism is like a transformation. So I guess you can transform one into the other and get the same thing. So it's like isomorphism.
Same under some sort of shape changing. Yeah, okay, go.
Yeah.
Okay.
Okay. So I've drawn another graph. So do people think that this one is planar? Can we redraw this graph on our flat page so that no edges cross?
I like these games. Okay, over to chat. So I guess, can I talk about the possibilities then? So if it is planar and if it's not planar.
Mm-hmm.
If it's not planar, that means that however you move the corners around, there'll be some things crossing, which is weird. I can't really imagine that. And if it is planar, there's some way to move the corners around or move the edges around, redraw the edges, maybe move some points so that none of the edges are crossing. And that also sounds hard. So I'm kind of impressed. I'm impressed either way.
Yeah, so if we just kind of think about this problem, it would probably be much easier to show that a graph is planar, because we could just redraw it. But if we want to show that it's not,
I think both of them involve being clever in some sense, right?
Yeah.
I can't see any shortcuts. It's not the case that you can, I don't know, count the corners, or maybe. Ooh. I'm spitballing while we wait for chat to get in. Chat has got a variety of opinions, including some people who have seen theorems about planarity before, who are, I think, playing quite a different game, which is have you seen this bit of planarity before? Fine, okay. And some people saying whether it looks planar or not. And Maya's just changed their mind to no. Imo votes no. Matthew votes doesn't look planar. I think chat's not convinced on this one.
Yeah. So chat's right. So this is actually not a planar graph.
Okay,
so this is called.
Okay, how are you going to convince me? Okay.
So this is called the complete graph on 5 vertices, K5. And it's not planar, but showing that it's not planar is kind of a hard problem. So we can prove it using something called Euler's formula, which tells us about the relationship between the number of vertices, the edges, and the faces or enclosed regions of the graph. So Brownie points to the first person who can paste Euler's characteristic formula in the chat. But this is going to be a homework problem because we're going to be talking about the utilities puzzle, which is another graph that may or may not be planar. And we're going to be solving it using topology. So before we talk about the utilities problem, and I was hoping that the K5 would get people curious and be like, I want the solution. So before we talk about the utilities problem, let's go back quickly to graph theory and like why we should care about graphs. So as we can tell, it's not always, graphs are pretty simple objects, but it's not always easy to reason about them. But they come up in computer science a lot. So when we're using Google Maps, for example, has anyone ever tried to, also I'm seeing some formulas in the chat, the v plus f, yeah, equals 2 is correct.
So fastest finger. Anonymous. Somebody anonymous may have claimed the brownie points of being fastest. Yeah, they've got various numbers
high five
on.
For you.
Yeah, so what number you got on there?
Yeah, okay. So that number. So Euler's formula, without getting too into it, it seems so simple, but it actually has deep roots in mathematics because it can be used on polyhedrons and things that are not just necessarily graphs. So it's really something worth reading about. But okay, so graph theory, Google Maps, directions. So if you've ever used Google Maps for directions, graph theory helped you find the shortest path from your house to the ice cream shop. In linguistics, graphs are used to parse trees. And trees are graphs that kind of look like this. So this would be a tree, for example. They're used to represent networks of communication. I mentioned the internet. We mentioned Facebook. They're also used in chemistry. So for example, a molecule is a graph, that. And they're also used in biology to model metabolic networks, which I'm not even going to try to draw because they're pretty complicated. So we're going to keep things fun, though. We're not going to do biology or chemistry today. We're going to do math and puzzles and games. And we're going to do something called the utilities puzzle. So the origins of the puzzle are unknown, but we know that it's been around since at least the 1900s. And when it was written about in the early 1900s, the guy said that it's been around forever. So we can deduce that it's been around for a long time. But this is the general idea. So we are going to draw 3 houses. So we're going to have a house here. We're going to call it H1. A house here, which we will call H2. And a house here, which we will call H3. And we have 3 utilities. So we have gas, and maybe I'll draw these in colors. So we're going to have gas, we're going to have water, and we're going to have electricity. And the goal of the puzzle is to connect each house to each utility without letting any lines cross. So let's try to do that. Well, we know that house 1 is going to need gas. We know that house 2 is going to need water. Well, house 3 is going to need electricity. House 3 is also going to need water. And house 2 is going to need gas. And okay, so now we have to start to move things around. So we know that house 1 is going to need water. House 1 is also going to need electricity. Well, house 3 is going to need gas. And now we start to run into problems because house 2 needs electricity, but there's no way, at least the way that I've drawn it, that we can connect house 3 to electricity because we get a line crossing here. And even if I were to draw it here, I'm going to cross the line. So the question of the utilities puzzle is, can I draw this graph on a plane such that none of these edges intersect? And if we go back to our talk about planar graphs and some of the graphs that we were looking at earlier, what we're essentially asking is the question, is this graph planar? In graph theory words, this is a bipartite graph on 3 nodes, complete bipartite graph. Okay, so we're going to be solving it, and people can maybe have a little vote on what they think, if this puzzle is solvable or not. But we're going to
be sorry. Yeah. Well, if you want the vote from chat, they're already chatting about it. On screen at the moment. I love chat so much. In the chat are discussing how you could get around this with sort of various ways of modifying where the edges are. But I think if chat's on the same trajectory as me, then if you've seen this puzzle before, you've maybe seen it but not seen like a reason why or a reason how to solve it or how to not solve it, as well. If you're like me, I don't know. Maybe chat's already miles away and can solve utilities in 5 dimensions or something, forwards and backwards. 27 of each. Let's go.
Also, an interesting perspective, actually, because okay, I'm not going to jump ahead of myself here, but when you say solve utilities, exactly.
I'll stop mentioning higher dimensions. Okay.
Yeah, topologist gets too excited.
I think it's fair to say the chat is not convinced that you can. Maybe this is testament to your attempt, that you attempted to join them, and that last green line is sad. It's got nowhere to go, and of course it's not a proof to try really hard. I tried my best, but I failed. Not a proof, but convincing enough for chat at the moment, I think.
So we're all convinced that this utilities puzzle is not solvable. But now the question becomes, how do we actually show that? Because there's an infinite number of ways we can draw this graph, right? We can move vertices around anywhere, we can move edges around anywhere, and we couldn't possibly dream of trying every single case. So we need to be more clever about how we solve this problem. And this is where one of my favorite fields of math comes in, and that's topology. And we're going to be using some ideas from topology to solve the utilities puzzle, which is a graph theory thing, which is traditionally in the domain of a computer scientist, or at least very often is. Mathematicians also work on graph theory, but you know, two sides of the same coin. There's so much interaction between math and computer science. So let's talk about topology. So topology is the study of geometric spaces that are preserved under what we say are continuous deformations. So intuitively, that means things like stretching and rotating or bending, but that means not tearing, not gluing, not cutting holes or poking holes in a shape. So I assume that a lot of you will have done some geometry before. And we can all agree that a circle and a triangle are not the same thing, right? These are two different shapes. Well, surprise to a topologist, they're actually the same thing. Because if we're free to bend things around, if I were to take, what do I have here? I have a hair elastic, for example. If I were to start with a triangle, really terrible triangle, then I could like stretch it out and turn it into a circle. And so this bendy shape to a topologist is all the same thing. So shapes are flexible things in our eyes, which is really cool. So for example, if I have, and this is sort of a running joke, is if I have a donut and a coffee cup, even though they look very different on the outside to a topologist, they're actually, yes, as James is holding his mug, they're actually the same shape to a topologist because it's just this one surface with a hole in it. And so in math lingo, we say that these two shapes are homeomorphic, meaning they're like topological twins. So they might look different on the inside, but they share certain fundamental structures. So if we could picture, for example, a donut, just so we know what we mean by homeomorphism, we can sort of, this is going to be a serious test of my art skills. We can turn it into a mug.
I think your art skills are already better than average for the live stream. Yeah, that's a mug.
And then something, we might have something in between that kind of looks like this. A much bigger hole. Yeah, something like that. So we could sort of stretch it out and press the hole out. Right, so the important word to remember here is, I'll use a darker color, is homeomorphic. And remember that homeomorphic means topological twins. So we have this continuous deformation or transformation, I should say, from one object to another. So topologists are interested in surfaces, like the flat screen that you're looking at. And so we talk about graphs as they're embedded in a surface. So when we're drawing graphs, we care that we're drawing the graph, for example, on the flat screen. And yeah, so let's talk about how a topologist would define a graph. Because the first definition that we used is the one that you will probably see the first time you ever maybe take a course in graph theory, and the topological definition is one that comes later, but it's very similar. So we say an arc. How are we? 5:30. Okay. So an arc is a topological space that is homeomorphic to a closed unit interval. So what that really is saying is that its topological twins to, for example, 0, 1, a closed. And that is simply an interval that includes its boundary points.
So a little bit of the number line, right? A little bit the numbers between 0 and 1.
Yeah, exactly. So that interval is all of the real numbers between 0 and 1, including 0 and 1. And so mathematically, even though these things look different, topologically, they are to us, they are the same. And so we would call the endpoints of A. So an arc can be something like this. We can have an arc A, and we'll call these points P and Q. And the endpoints of A are these points such that A minus P and A minus Q are connected. And so intuitively, that means if I take my arc and I remove these points at the end, I still have one connected piece. However, if I were to remove any other point, like a point in the middle here, for example, then I am disconnecting my arc. And so I cannot call that point an endpoint anymore. Okay. And so a finite linear graph, from a topological point of view, is just the union of finitely many arcs, which intersect in at most a common endpoint. So a finite linear a finite linear graph, and I'll talk about what I mean in a second, is written as the union or the combination of finitely many arcs. So we take a bunch of these arcs, a bunch of these pieces, and we connect them in such a way that they touch each other only at their endpoints. Each pair of which intersect at only their endpoints. So I might have a bunch of arcs, endpoints. So I might have arcs like this. Suppose I have an arc A, and then I want to take a union with another arc, but I can only intersect it here. I might want to add another arc. I can only intersect it there. And we look at this definition pairwise. So for every two arcs, we look at those endpoints. And so we call the arcs edges, and we call the endpoints vertices. And so this definition is very similar to the definition that we talked about earlier, but we take the perspective of a topological space that is sort of topological twins with this interval. And we talk about how we can take unions and intersections instead of using the language of set theory. And we also care about how this graph sits in some other space. So in this case, a plane, which is my tablet screen that I'm writing on, or the computer screen that you're looking at. And so we say a graph is embedded in this space if all of the vertices are distinct elements. So we don't want to have copies of vertices. And an edge is an arc connecting two endpoints such that no two edges intersect except at possibly their common endpoint. And so this is the topological definition equivalent of being a planar graph. So we just have this topological graph sitting on the plane where none of our edges are intersecting. So I just want you to think, okay, this is what a topologist is defining to be a planar graph. Okay, so I assume hopefully that people more or less have an idea of what we mean by graph from a topological perspective. As long as you get the general idea, you should be okay to follow the rest of this.
I'm trying to tell if people have I'm not sure we've used the word union recently, but I've remembered it's a normal English word as well, right? For like the collection of things together.
Yeah.
So what you're saying, I think, or maybe my understanding so far is that, okay, topologists also have different words for edges and vertices, the endpoints and the arcs, or the arcs kind of include the
Yeah.
endpoints, I suppose, but there's this
Yeah.
corresponding language between
Yeah.
what topologists say about their collection of things that are homomorphic to each other, lets them do the deformations, versus how maybe graph theorists maybe not to think about where the edges live at all, just that things are connected by
Yeah.
edges.
Okay. Exactly, yeah. So graph people, we like to use like sets to define things. So we just think of the vertices as, bag of objects. And union is also just a word in English, but mathematically a union is when you take everything in one set and everything in another set, and you smush them together and drop any duplicates.
Is it the OR operator in computer science to say this or
yes.
that? Yeah, okay.
Yeah. So to a computer scientist, and actually set theory comes up loads in computer science as well, taking a union is like taking an OR statement. So if I have a set A union B, then that means that any elements I know is going to be either in A or in B. So I don't necessarily need it to be in both, but I need it to be in at least A or B for it to be in the combination of A union B.
Cool. Okay.
All right.
I think we're bored. I think I've stressed too much about the word union. Sorry.
It's okay. Yeah, maybe an introduction to set theory can be an episode that we do as well, because that's a good one.
Really wants to do set theory. Okay, good. Sorry, carry
on. Okay, so let's talk about a cool topological space called a theta space. So a theta space, and now we're going to sort of start to go back to our utilities puzzle. A theta space is a topological space that is the union of three arcs, is the union of three arcs, and let's give these arcs names. So we'll call them A union B union C. So our arcs are A, B, and C. Each pair of which intersects in precisely their endpoints. And note the difference in the definition, each pair of which intersect in precisely. So we talked about what endpoints were, and note the difference in the definition between this theta space and just a graph embedded in a plane. So when I talked about a graph embedded in a plane, I said that they can intersect in at most their endpoints. So they can, but they don't necessarily have to intersect in their endpoints. In the theta space, we're specifying that they intersect in precisely their endpoints. So that means that we have three arcs. So I might have one that looks like this, and I'll call it A. And I might have another one that looks like this. I'll call it B, and it's intersecting A in precisely its endpoints. So we have to have those intersections. And I might have another one called C. This is C, and C intersects in precisely its endpoints here as well. And so can anyone guess why this is called a theta space?
I thought it was a cool name. But I also thought, until you drew the picture, I thought this was going to be a triangle. Whereas I hadn't twigged that you want each pair of the arcs or edges to intersect in kind of both of the endpoints. So you've had to draw this thing with three lines all going between the 2 points. Yeah. Anonymous has taken it first as looks like the Greek letter theta.
Exactly. So this is actually homeomorphic to, or topological twins with, the Greek letter theta. Good job, Anonymous. Nice. Yeah. So you will be a master of the Greek alphabet if you decide to study math. Just as a byproduct.
Okay. So is this the effect of joining? How's this going to come up, I wonder? You've got two things that are joined by three edges. And okay, that doesn't happen in your graph though, does it? Because you said way ages ago that we were going to do simple graphs that are only joined by one edge at most. And this one seems to be like a graph where it's joined by three edges between the same endpoints. Is that?
Yes, so we're going to be using this to solve the utilities puzzle.
Okay. I'll let you do that.
But, yeah. Yes. So with the topological definition of a graph, we do allow, in this case, multiple edges between 2 points.
Okay, yeah. Fair enough.
So that is a good observation. Yeah. So, okay, in the interest of time, I'm going to basically, I'll talk a little bit more about some like topology ideas, and then we will get to how we use this to prove the utilities puzzle. So there's a number of things that we define in topology, and the idea is that we're interested in studying spaces and how we might separate spaces or how things are connected. So just for a terminology, a simple closed curve is a space that's homeomorphic to the unit circle S1. So my elastic band that I had earlier is a simple closed curve. So we call this topological twins with full closed curve is homeomorphic to our circle, which we call S1. And basically, topological spaces are built up using something called open sets. So I'm not going to get into the definition of them. Maybe I'll do that next week if we want to talk a little bit more about topology and less about graph theory. But we can think of open sets as topological building blocks. And we can use certain ideas that are intuitively, they feel obvious, but mathematically are sometimes hard to prove, using the language of topology and open sets. And one of these ideas is how we can separate a space. So given a space X, a separation of a space is a pair of disjoint non-empty open subsets whose union is X. So for example, if I have a space X, then a separation of X might be two pieces like this and like this, which I might call U and V, such that taking them together, I get my entire space X. But if I take their intersection, then that is the empty set, meaning that there's nothing that lies in both U and V. But if I take them together, then I get all of X. And so we say that a space is connected if we can't separate it into two pieces, U and V. And essentially, let's see, so I have about 10 minutes. So we can talk about separation theorems and how we can separate different spaces into different connected components. So an example of such a theorem would be, given a sphere like this, if I draw an arc on the sphere, do we think that an arc would separate it? Suppose this is my arc. So is this separating my space?
Let's give them a moment. So
yeah,
I guess if you have, are you talking about the points on the surface of the sphere, whether
yes,
they've been sort of separated into two different bits by the by the arc that you've drawn on?
Yes.
Because I guess you can go all the way around the arc. So
yeah.
I guess, okay, so you're talking about the separation of the space as the, okay, so the space is like the underlying thing, like your computer screen that your graph's drawn on, as different from the graph itself. It's sort of some edges or arcs and some vertices on top of that space. And it's whether or not your graph splits up or separates that that space
Yeah.
into different bits. Yeah, people just say no. This doesn't
No.
split up at all. You go around it, right? It's all joined up still.
Yeah, exactly. So people in the chat are correct. So if I just draw an arc on my sphere like this, I am not separating my sphere into two disconnected components, right? Because I can intuitively, take a path and go around and sort of I guess yellow is a terrible topology sphere.
You can go around. If you drew a
Yeah.
bigger graph, then probably it would start separating up the sphere into different.
Well,
bits.
yeah, it depends. It really depends on your space and like how you're separating it. So, for example, another separation theorem, which is very intuitively simple, but not so easy to prove, is called the Jordan separation theorem. And basically, I'm given a sphere, and if I let C, so I'll use C. If I let C be a simple closed curve, then C does separate the sphere. So if I were to draw a curve like this on the surface of my sphere and call it C, then now I am separating my sphere because I have this interior here, and I have everything that lies on the outside here, right? So this is a separation. And essentially, we can use these separation theorems to reason about, the space that we're looking at. So I was going to run through a proof about separating the sphere, but instead I'll quickly talk about how the sphere relates to the plane, and then I'll talk about the utilities puzzle. So the nice thing about topology is that it can give us different perspectives of solving the same problem. So we've been talking about the sphere for the past two examples, and we've been talking about a theta space, and one might ask, why are we doing all this? Well, the answer is that we can actually embed the plane or the screen onto a sphere. Meaning if we can solve the problem on our sphere, we can also have a solution on the plane. And you do that using something called stereographic projection. So the idea is that you take a sphere like this, and from the very top, the North Pole, you shine a light down through the sphere like this. And that sphere is sitting on a plane that looks like this. And the beams of light coming from the North Pole are intersecting our sphere at exactly one point. And we can hit every point on the plane with this beam of light, with the exception of the North Pole, because that is where we stuck our light. And so if we solve our puzzle on the sphere, we can sort of project it down onto the plane and have a solution on the plane. So this is called stereographic projection. There's a lot of really cool YouTube videos of people using actual lights and spheres and doing this. So I do encourage you to check it out because they're fun to watch. The stereographic projection. And this is just one of those many cool things we have up our mathematical sleeves for solving puzzles.
Okay, so if you remove a point from the sphere, then you can kind of unwrap it in this manner, unwrap it to be like a plane. Which, if you're allowed to bend stuff, that's fine. Okay, so a sphere missing a point unwraps into being topologically
exactly
a flat plane. Okay.
Yeah, so that's sort of the picture you can have in your brain.
Okay, so that means
and so what we're going to do is we're going to try to solve the utilities puzzle on the sphere rather than the plane, and then use that to deduce a conclusion about the utilities puzzle on the plane. And so the main lemma that we're going to need to use is that our theta space separates the sphere into three components. So a theta space X separates the two sphere S squared, so that's what we use to denote the sphere, into three components. And I will draw a picture so we know what I mean by that. So I can have my sphere like this. And I might have, so let's assume, we'll say this is my sphere. And I can embed my theta space like this. So I might have my arc A going around the top of it like this. I'll call this A. And I will call this B. So it goes around the side like this. B. And I will call this last arc, we'll call this C. And hopefully my drawing is clear enough that you can see how this is the theta space that we were talking about earlier. But I'm just taking this sort of thing and I'm sticking it on my sphere like that. And so we end up with these three components. We have a piece here, a piece here, and a piece down here. Okay. And I was originally going to prove this today, but seeing as I'm running out of time, we're going to jump to the utilities puzzle. And what I'll do is I will send James a copy of the proof that this separates the sphere into three pieces. So for those people interested, they can have a look. And maybe he can put it up online somewhere, or I can, but FYI.
Further reading notes on the Oxford Maths Club website. Check the link at the bottom, but give me a couple of days to actually put them on the website, please.
Yeah.
I'm really behind with the further reading. Sorry, everyone. Yeah, good. Okay.
Yeah.
Utilities problem. So if I accept that when you draw a theta on a sphere, you get three bits: the top bit, the bottom bit, the kind of outside of the theta, and counts as the third region on a sphere. If I accept that, which I feel like I can accept that, then you're telling me that. Okay, so does that shape turn up somewhere when you do the utilities problem?
Yes, it does. We're about to.
Okay, you're forced to have a theta space. You're just trying to plumb water into the houses or whatever, and you're forced to create a theta space.
Exactly.
I really can't imagine where it's going to be.
Yeah, so we're going to turn our utilities graph into a theta space. So let's quickly redraw it. So we're going to call this H1, H2, and H3. And we're going to call this gas and water and electricity. And okay, so let's think about how we're going to construct our theta space. So we're going to let arc A be, and note, so we need every house to be connected to every utility. So we know that these arcs are going to have to exist. So we're going to let arc A be the line that goes from gas to house 1 to water. And we're going to let arc, so actually let's draw that first. So we're going to have arc A, let's say going from house 1 to gas, and then going from house 1 to water. Okay. And we're going to let our second arc be the line connecting house 2 to gas and water. And we know that house 2 is going to have to be connected to gas and water. So we're going to do this. So let's connect gas to house 2 and then extend house 2 up to water. And then we're going to let our final arc, C, be the arc connecting house 3. So gas to house 3 to water. So we've got 2 out of our 3 utilities. And we know that these lines are going to have to create a theta space on the sphere. But now we have this third utility to worry about. Okay. So we have three arcs that are intersecting in only their endpoints, which are here and here, right? And so we have that Y, which is the union of A and B and C, is a theta space. And so by our lemma from before, by what we talked about up here, we have that Y is separating the sphere into three components. So we'll say if this is Y, we'll call one component, for example, U, and we call one component B and one component W. So we have three components, but for ease of diagrams, we will draw them down here. So let's call this component U. And we'll call this component V. And remember, these are just the components that are corresponding to the three pieces that we got in our sphere. And we'll call everything else on the outside, we'll call this W. So everything else that is not in these two components is W. So, okay, let's think about our electricity. Well, we know that E is going to have to lie in the closure, or is going to have to lie in one of these components, because otherwise that means we would have four components, which is a contradiction. We know that we only have three. So that means if we don't have lines intersecting, then E lies in closure one of these components. So if we don't have lines intersecting, this implies that the line from the electricity to house 1 and the electricity to house 2 and electricity to house 3 are going to also have to lie in that same component. Right? Because if an arc lay outside that component, well, this would contradict Y's separation of x squared. So that means that we could have a path through pieces that we claimed we could not have a path through. And so if we look at our diagram, well, E can't lie in the closure of U because that closure does not contain the third house. So if we look at this component here, we know that we can't have an electricity node in that component because this house here is on the outside. And we can use the same reasoning to look at all three of our components. So I can say, well, electricity can't lie in this component, component V, because house 2 is outside that component. And similarly, I cannot have my electricity lie in W, which is this region on the outside, because my second house doesn't lie in that component. And so no matter how I draw my electricity node and the arcs connecting it to every house, I'm going to have a line crossing components. And so we reach a contradiction, and we say that this graph, X, can't be embedded in the sphere. And therefore, by stereographic projection that we talked about earlier, can't be embedded in the plane. And so we basically use this topological argument where we've constructed a theta space, a topological object, modeled our graph after this topological object, argued about how it can separate a sphere, and then said, well, it can't live in a sphere, so therefore it cannot live in our plane. And we have used topology to solve a problem in graph theory at a very high level. So I think that's awesome. As a computer science student, I never really thought that this very abstract notion of bendy shapes could have anything to do with a utilities puzzle. So yeah, I thought it was cool. And I am out of time, but there are other ways to solve this problem too. One of which is by counting vertices and edges and faces and seeing how those relate and using Euler's formula. So there's loads of things or loads of approaches, but this is one of them.
I'm going to set them some homework. I'm just going to connect my pen. It's going to make a noise. There we go. I'm not sure if Alice could hear the connection noise, but that's a connection noise for you at home. Okay. So I saw some people in chat earlier saying that on a donut. Wait.
Yes.
On a donut, they know or they've heard that you can do the utilities problem. You can connect these 3 houses to 3 utilities with none of the lines crossing. Here's a challenge for you at home. If you've seen that, but it hasn't, maybe you've seen how to do it or you've had a go, at some point in the proof that Alice has done, something's got to be different, right? Because Alice has proved that you can't do something, whereas on the donut you strongly suspect that you can, because Matt Parker has given you a mug or something. We'll put a link in the further reading to Matt Parker's website to get a mug with this problem on. Apparently on a mug you can do this, which must mean that maybe when you draw a theta on a torus, it doesn't split the torus into 3 parts. And that's a bit of a weird thing to say, because obviously if I just draw a theta on a torus, there's 3 parts, 1, 2, 3. It separates it into 3 regions. Here, one of them's really large, but two little regions. So, but maybe there's a different way to draw a theta on a torus, and only get two regions, which is a bit weird. Something we accepted as pretty obvious, that when you draw a theta on a sphere, you get 3 regions, 1, 2, 3. Probably shouldn't draw such a curly theta. When you draw a theta on a sphere, you get 3 regions. Maybe on a torus, it kind of depends. There's definitely ways to do it where I get 3 regions. Maybe there's a way to do it where you only get 2 regions, and that lets you then put in the electricity and connect it to all of the houses. Without 4 or and then separate homework question, I guess, is if you can connect 3 houses to 3 utilities on a torus, can you connect 4 houses? Can you do, it would be called K4 for connecting 4 houses to 4 utilities. And if you can you do K5? And if you can, 6, and so on. How many houses can you connect to how many utilities before you run out of space in that space? I don't know, homework for people who have seen torus extensions before.
Yeah, how far can we generalize?
How far can we go, right? Okay, maybe the torus buys you some more space by sending utilities on this weird journey through the whole of the torus.
And if you don't have access to a torus, you can take a coffee mug at home and draw utilities and houses on your coffee mug and try to solve it on a coffee mug.
Right. Well,
they're the same.
Okay, smashing. I've just seen Rory's got to go. I think I've got to go. I think Alice has got to go. Alice, you're back next week, I think you said.
I am
back next week for more computer science takeover. So we'll see you next week. And we'll see people watching in chat as well, I suppose. That's right. We always say we'll see you in 167 hours. Thank you, Alice, for appearing on Computer Science Takeover.
Thanks for having me.
Thanks for watching. We'll see you in 167 hours for another episode of the Oxford Online Maths Club. Take care.
Awesome.
Bye.
See you then. Bye-bye.